All right, welcome once again to another new course which is named Applied Electricity. So, as the name suggests, it is a branch of physics, specifically electricity, where you are looking at the flow of current within an electrical circuit and how to calculate the current passing through some elements of the circuit. We know that circuits are made up of elements, which are the loads. And some of the loads are passive loads, some are active loads. Active elements or active loads are loads which can generate energy or produce power, but passive ones can store or only what dissipate it. So now dissipate it as heat. Yes, dissipation as heat. So now let's look at our first lecture, which is the chapter one, and this is basically straight from secondary cycle. We know these basics from the secondary institution or secondary cycle institution. All right, so now let's go into let's dive into it. Okay, so now let's go. So basic definitions and circuit laws. This chapter deals with the basic definitions, concepts, and laws that are associated with electric circuits. As I said, the specific laws under consideration are: we are going to look at Ohm's law, Kirchhoff's current and voltage law, what we call the KCL and the KVL, and applications of these laws. Basically, that's what I said. That's the main idea of this whole course. So circuit elements, of course, you know that they are the loads. Of course, there are two types of elements in a circuit: the active or the passive. So these ones are readings. They are readings. So active elements are capable of generating electrical energy, power, as I said. In other words, they are acting as sources of energy in the circuit. So cells, batteries, solar modules, generators, microgrid solar modules, all of these ones are all active elements. They are active, they produce energy. Then what is electrical current? It's just an electron in motion or electrons in motion. So current can also be defined in terms of the quantity of charge over the time flow. So the rate at which electron or a charge is flowing with respect to time is what you are calling current, right? Yes. So potential difference PD, you know that it's just the change in what? The change in what do you call it? Voltage, potential difference, right? Between 2 points in a circuit. Yes, when there is change in voltage, that's the flow of electrons from higher voltage to a lower voltage. Whenever there is change in voltage, there is potential difference, or what we call EMF. EMF, right? Yes. So EMF is the force that drives that particular current from that higher voltage source to that lower voltage source. So the force is called the EMF, and that difference is what we call the PD. So EMF drives, or EMF more or less like bring about that PD flow, Alright, so that's by the way. And passive elements are elements that cannot produce energy, but they are able to store the energy that you give them and dissipate it as heat or whatever, or to other materials, right? Alright, so resistance, capacitance, inductance, they are the properties. And the elements themselves are the resistor, capacitor, and what? Inductor. So all these ones are to be known by you. Alright, so this is a circuit showing inductor here, which is a passive element, resistor, which is a passive element, and a voltage source, which is a what? Which is a what? Active element. Then battery two, which is an active element. So this circuit is connoting both passive and what active elements. Let's look at what resistivity, conductance, and conductivity to are. So resistivity, you saw it in physics back in the days, SHS. So we said that resistance is directly proportional to R is not resistivity, it's resistance. We said that resistance is directly proportional to the length of the conductor or wire and inversely proportional to the what? To the area. To the area. So with this, if you want to remove the constant of proportionality, you bring equals to, then you bring a constant. You bring a constant. That constant that we bring is what you are calling the resistivity, right? So K is the resistivity in this case. Rho, rho, and it is known as the specific resistance or resistivity of the material of the wire. So every material that we use to make a wire has a resistivity. It has a resistivity, and the higher the resistivity, the higher the what? The higher the resistance. So that's resistivity of material, the resistance of material of unit length having unit cross sectional area, also defined as resistance between opposite phases of a unit cube of that material. So the unit is ohmmeters. 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 And if you want to know the unit, it's very simple. You just make resistivity the what? The subject. So if you make it the subject, you get AR over L. A is area, so meter squared of that particular wire, the cross section of that material. Then resistance is ohms, length is what? Meters. Meters cancel one of the meters, you are left with ohm meters. Alright, so now conductance is here. So the inverse of resistance is what? Conductance. So the higher the resistance, the lower the what? The lower the conductance. And it makes sense. Resistance is the opposite force to how well a current can flow through a material. So if the resistance is high, then it means the opposite force is high. So more current cannot flow. And if more current cannot flow due to high resistance, then it means your material is not that conductive. Are you good? Alright, so it makes sense. And the unit of conductance is Siemens. Siemens. This time not Siemens Energy as a company, but Siemens as a unit. And I know you are thinking of other Siemens as well. Are you good? Yes, it's not that Siemens. Sorry. It's a Siemens measuring the conductance of a material. Period. Alright. So we have fun a little, then we learn a little, right? So we have what we call the conductivity itself. So you go to the industry as an electrical engineering man or as an electrical engineer or any specialist, engineering specialist, they ask you, so what's the conductivity of the material? What do they mean? They mean the conductance of the material per unit length of the material. So conductivity is measuring the conductance of a material based on the unit length. So it means that length can affect the what? The conductivity of a material. If that's the case, length can affect the conductivity of a material. Alright. So the higher the length and remaining conductance to be the same, the more lengthier a material is, then the lesser it what? Conductivity. Alright. Alright. So now we have a relationship here. So J is equals to 1 over R, where J is the what? J is the what? The conductance. I said it up here. So we know that R is also resistivity times length over A. So if you should do this well, you get A over L times what? Resistivity. So it is A over L times 1 over resistivity. And this 1 over resistivity is what we are calling the what? the conductivity. It is represented with what? It is represented with this symbol here, this one. Are you good? All right, so now that's what you should know. The unit is Siemens per meter. Siemens per meter. All right, so if I give you resistivity, you should be able to find me the what? The conductivity. You just find the inverse of that. Then you have what we call branch, loop, and node. Some of you don't know the difference. So a branch represents a single element such as voltage source or resistor. That's largely a branch represents any two terminal elements. Are you with? So when you talk about branch, you are just talking about wherever there is a voltage source or a resistor or any load in the circuit, a single element. Look at the weight. Look at the indefinite article a, right? So a a. So now here can be a branch, here can be a branch, here can be. Will here be a branch? All right. Here is a branch, here is a branch. Then a node. A node is a point of connection between two or more electrical two or more circuit elements, right? A node is a point of connection between two or more circuit elements. So if that is the case, two or more circuit elements, then it means this 10 ohms and this 30 volts, they are two what? Electrical elements which can make B to be a node, because they said a node should join a connection between two or more. And this is two. This one here and this one here. So B is a node, C is a node, 10 ohms, 15 ohms is a node. D, yes, D2 can be a node because when I come here, 20 is here. Then if I extend this line, there is 10 ohms here. So 10 ohms and what? 20 ohms. So it means there can be a node in between a node. That's what it means. Then this E here too is a node all the way from 10 ohms and 5 ampere source. This is the current source. The 5 amperes is a current source. So you should know what a node is. All right, so that's by the way. Then you have the loop. A loop is a closed path in a circuit. So BCHAB loop, you start, you end there. BCHAB. I started with B, I end at B. So this is a loop. CDGHC. This is a loop. DEFGD. This is also a loop. And I know why I'm explaining this to you, because in our successive or subsequent lectures, I will be going straight. I'll be flowing like water, right? Yes, so you should know what a loop is. These are relationships for the passive element. You know what a passive element are. So for resistance, that's the expression. You know this from what? Ohm's law. From inductance and capacitance, these are the formulas. Are you okay? Alright, so L is the inductance, C is the capacitance. The IDT is just change in current per time. Are we good? The VDT, change in voltage per time. Alright. There are two laws governing any electrical circuit. The first one is the Kirchhoff's law. Of course, is the current law of Kirchhoff. We call it KCL. And it states that the algebraic sum of the current entering or leaving a node at any instant is zero. So algebraic sum, it means plus or minus. Algebraic means plus or minus. Leaving a node at any instant is zero. In other words, the sum of the current entering a node is equals to that sum leaving the node. So if I have this here, let's assume this is a node here. It's a node. Then what we are saying is I1 is what? I1 is leaving the node. I4 is also leaving the node. So these ones are the leaving ones. The sum of it should be equals to the one entering. I2 is also entering, and I2 is also entering. So this is what we get. I1 plus I4 equals I2 plus I3. When they've given you some values, they are saying that if I1 is 4, I2 is -5, of course, amperes, current is amperes, the unit is amperes. I3 is 1 ampere. We should find what? We should find what? I4. So from here, if we should make I4 the subject, I4 will be equals to I2 plus I3 minus I1. So I4 will be equals to -5 plus 1 minus 4. So I4 will be -4 minus 4, -8 amperes. That's the value for I4. Then have what we call the Kirchhoff's voltage law, KVL. It's saying the algebraic sum of voltage around a closed path or a loop in a circuit at any instant is 0. Are we okay? So this can be expressed in another form. We can also say that the sum of voltages is equals to the EMF. Algebraic sum of voltages is equals to the EMF. So it's either you find all the voltages algebraic sum, then you equate it to 0, or you find the EMF source, or what we call the voltage source, then you equate it to the sum of the voltage drops, and voltage drop is given by current times resistance. We saw that from the relationship in the passive element. So voltage drop across a resistance resistor is I times R, current flowing through the resistor, times the value of the resistance. So let's use that idea to find the value of Vs here. So here I will choose any direction of current flow. So let's assume it is clockwise. So here what you do is that I'm using the sign convention where the current leaves the voltage source is what I'm going to use to assign the sign of the voltage source. So you see that with this clockwise I've chosen, it means current will flow from negative terminal and leave from the positive terminal of Vs. Are we looking at that? It's entering at minus, leaving at Vs. And I said I'm using the leaving terminal. So the leaving terminal is positive. So that will make positive Vs. Here it is entering positive, leaving negative. So minus Vr. Here it is entering positive, leaving minus. So where it is leaving, minus Vl. Then what did KVL say? It says that the sum of all these algebraic sum of the voltages should be equals to what? 0. So with this, I'll get Vs is what you are looking for. Look at the question. You should find the value of Vs. So Vs, which is positive, minus Vr. Vr is given as 15 volts. Minus Vl is given as 6 volts. Should be equals to 0. So Vs will be 15 volts plus 6 volts. Vs is 21 volts. Are we good? Yes, we should be good by now. So now Ohm's law, of course we know this already. They are saying that current is directly proportional to the voltage, provided temperature remains constant and the material is a what? It's a conductor. That's all. So this, we know this already. So Ohm's law brings about this formula, V equals IR. What is a series circuit? If we have a circuit and the current flow in each of the circuit elements are the same, then that circuit is called what? A series circuit. So what it means is, in this circuit, the current, so this is the conversion they use, clockwise. The current through R1 is the same as R2, is the same as R3, is the same as R4. which means that then what you are going to do is that if you want to find the total resistance in a series circuit, it is just the summation of each of the resistance depending on the number of resistors you are having. You sum all of them. Then instead drop the voltage drop across each of the elements in a series circuit is different. Is different. I mean the voltage source across or the voltage drop across R1 is different from the voltage drop across R2, is different from the voltage drop across R3, is different from the voltage drop across R4, simply because the resistances are not the same. Alright, so with that, you should get in mind what a series circuit is. So basically, this is what I said. The sum of the current is given by the same thing. So the sum of the current in this circuit is the same current passing through R1, is the same current passing through R2, is the same current passing through R3 and R4. So voltage in series circuit is rather different. That one you add them. If you want to find the total voltage in a series circuit, you add the voltage drop across or the PDs across R1, R2, R3, R4. Are we okay? Yes. So I have an example here and we would demonstrate what I said with that example. Alright, so the voltage source is what? 100 watts, 100 volts, and the current source is 2 amperes. The current source is 2 amperes. Uh, 5 ohms, 15 ohms, 20 ohms, and 10 ohms. So we should calculate the total resistance, which is RT, or people call it net resistance. So it will be R1 plus R2 plus R3 plus R4. So RT will be equals to R1, which is 5 ohms, plus R2, which is 15 ohms, plus R3, which is 20 ohms, plus R4, which is 10 ohms. So RT will be equals to this plus that. So this is 20 plus 20, 40, 50 ohms. 50 ohms is the total resistance, right? But by the same way, you can also use the Ohm's law to find the total resistance, because total voltage is equals to total current times total resistance. So if I want total resistance, it will be total voltage over total current. But total voltage is the 100 volt source, and total current is the total current source, which is 2 amperes. So 100 over 2 is 50 ohms. Don't forget, volts per amperes is the same as ohms. Alright, so that's how to find that. Then you have something we call the voltage divider. That's something we call the voltage divider. So voltage divider is as a result of series circuits having different voltages across them. So the voltage across R1 V1 is different from voltage across R2 V2, voltage across R3 V3, voltage across R4 V4. These voltages are different. So imagine if you want to find the voltage across R1, which is V1, it will be the resistance continue. I've been busy a little bit, that's why. So now, with this voltage in the resistor 1, the resistance there in resistor 1 is 5 over total resistance, which is 50, times the total voltage, which is 100. So 50 goes into 100 two times. So I'll get 10 volts for the voltage across R1. So that's how we find the voltages of circuit elements in series circuits. We just find the ratio of that resistance to the total of the resistance times the total voltage. That's basically the idea of, so you see I had 10 volts. So basically that's the idea of voltage divider rule. Voltage divider rule. So voltage divider rule is for series circuits, because you know that for series circuit voltages are different. So when you come to parallel circuits, what is different in parallel circuit? It is what? Current. Current is different in parallel circuit. So in that case, we'll be using the current divider rule. So this is an example of a parallel circuit. It means that the current passing through this branch is different from this branch, is different from this branch, is different from this branch, is different from what is flowing through R3. So what is flowing through R3 is different from what is flowing through R2, is different from what is flowing through R1. And these are different types of parallel circuits. So you need to master them. So immediately you see a circuit like this, you should know this and this are parallel. Immediately you see a circuit like this and this are parallel. Immediately you see something like this and this are parallel, this and this are parallel. Simply because if current is coming from this voltage source here, let's say I, it's coming from the voltage source. When it reaches here, it will be different. So here will be I1, here will be I2. That's why we are saying they are what? Parallel circuits. They are having different currents flowing through them. Not that as for the not that as for the series circuit where the current are the same. But still we have something which is the same in parallel circuit. It is the voltage instead. So what it means is this voltage source will apply or supply the same voltage Vt through R1. It will supply the same voltage Vt through R what? R2. So it means that the voltage across resistor 1 is equals to voltage across resistor 2, which is the same as the source voltage. But the current across resistor 1 is not the same as the current across resistor 2, and this is not the same as the total current. Are we okay? Alright, so now this is by the way. So in power circuit, we use the current divider rule, as I said, and this is the formula for calculating the net resistance. So for instance, if I want to know the net resistance, it is 1 over RT. Don't forget, it is not RT, it is 1 over RT, because 1 over the first resistor, the resistance of that, plus 1 over the second resistor, the resistance of that. So what you have here, you equate it to 1 over RT. And what you have here is basically R1 plus R2 over R1 R2. If you want RT will be R1 R2 over R1 plus R2. So this is an expression for the net resistance of a two resistors in parallel circuits. You multiply their resistance, you divide it to their sum of the resistances. Are you okay? So product over sum. So imagine we want to find the net resistance of this. It will be 1 over RT equals 1 over 4 plus 1 over 6 plus 1 over 12. Then you find the LCM, 12, right? 3, 2, 1. We get 6 over 12 is equals to 1 over RT. If you want RT, you get 2. So that's how we find the net resistance. These are the questions you'll be seeing, right? All right. Then this is some. All right. So divider rule, current divider rule. So this time, the current divider rule says that if I want to find the current in maybe R1, I want to find a current in R1, that would be I1, right? the current in R1 will be I1. It is the opposite resistor, which is R2, right? It's not like in series circuit that is that same resistor. This time it's the opposite resistor, the resistance of the opposite resistor over the total resistance times the total current. The total current. So basically that's how we find the. So let's use this example here. So this we need to find the net resistance, which will be RT 1 over that 1 over 25 plus 1 over 45. Are we okay? So with this, RT will be equals to 25 times 45 over 25 plus what? 45. And let me look at the value for the RT. The RT will be, okay, so now I don't even need I don't even need the RT. I don't need to find the net resistance. I'll use this simple method because I want to find the current in each of the resistors. So let's assume I want to find the current in this resistor 25. It will be the opposite resistor, which is 45 over the sum of 25 plus 45 times the net current. And the net current is given as 14 in the question. So with this, I will get 9 amperes. And if I want to find the current in this, that one will be the opposite resistance, which is 25 over 25 plus 45 times the net current, which is 14. And that one is 5 amperes. So what can you see? You see that the current in this 25 ohms is bigger than the current here. And that makes sense because if the resistance is small, more current will flow through. That's why the current flowing through the 25 is bigger than the current flowing through the 45 ohms. So these are examples you can use, calculate, and find it for yourself. I will meet you again. But before I leave you, let me just give you a brief about electric power. Power is the work done per unit time, right? So it is given by current and voltage. So if you have current 15 amperes, you multiply it to your voltage, you get your power. This power is given, voltage is given, you need current. So 1000 over 120, you get 8.33. Here, efficiency is output over input. You know this. So you should be able to find the input power or the output power given the efficiency. Are we okay? Yes. So these ones are some expressions that we have for power, current and voltage. But we know that voltage is I times R. So it will be I times R times I. So power will be I squared R. But we have another expression for power. Power can also be written as V squared over what? R. Simply because I is V over R. So V over R times V is V squared on R. Alright, energy is the ability to do work. So power is equals to energy over time. Energy over time. So if you have energy is the same as heat dissipated, which is I squared RT. So it will be, so energy up here is the same as I squared RT over what? Over T. If that should cancel, you get your I squared R. Energy is the heat dissipated, the ability to do heat. And normally in electricity, the energy is converted to heat. So this energy can also be represented by I squared RT, representing the heat energy dissipated through electricity. Then you divide this energy with time. Time will cancel time, then you get what we call power, I squared R. So that's why power is V over T. Alright. So with that, you can be able to find the cost of any appliance. So the cost will be the energy times the rate of charge. The rate of charge. So if you want to find the cost of your electricity bill at your home, just find the energy, which is the power times what? Times time that you use to consume your appliance, the power the appliance need to operate, times the time that you take to operate the appliance. If it's a kettle and you are using 1 minute to heat your water, look at the power needed by the kettle, multiply it with the time. The answer you get, you multiply it with the rate of charge. Are we okay? Let's assume 1 kilowatt hour of energy is maybe 5 cedis. Then you multiply it with 5 cedis. So basically, that is the idea of electricity. I've summarized everything. So go watch the video, grab your first lecture, and let's continue with the journey. Till then, safe, and I wish you the best of success. Bye.